Good evening, everybody. Welcome to BrisScience. If you haven't been here before, thank you so much for coming along. BrisScience is the University of Queensland's free public lecture series on science, where we bring not just the best scientists, but also the best communicators to share their research with Brisbane. I'm your MC for this evening, Joel Gilmore. Before we start, I would like to acknowledge the traditional owners of the land on which we're meeting tonight and pay my respect to elders both past and present. And I would like to, of course, thank The Edge, who hosts us here every month. It's fantastic to be back, and make sure you check out some of the fun things they have in the foyer out there for the workshops that go on in the Maker Lab downstairs. Quick bits of housekeeping. As always, if you have your mobile phone, you can leave it on for Twitter, but turn it off for calls. We have a special way of asking questions at BrisScience, which is you can ask them over Twitter using the hashtag BrisScience. And we will be live tweeting throughout the night if you want to catch up on things later. But we also take questions via those pieces of paper you picked up on the way in. So at the end of the talk, we'll come down the aisles, collect those questions and ask as many as we can before the time runs out. After that, you'll have the opportunity to ask your questions of our wonderful speaker in person, outside over nibblies and drinks. So we'd love for you to stick around and join us, because science should be a cultural thing for the whole city, not just at a university lecture hall. I think that's all that we need to do to get started. So tonight, it is my very great pleasure to welcome Dr. Emma Kennedy, who is from the University of Queensland's Remote Sensing Research Group, where her expertise includes climate change and coral reef ecology. And of course, not only with her research, but Emma is passionate about the underwater world, including, obviously, again, the research, but also working as a scuba instructor and writing for the BBC Wildlife magazine in the past. And tonight, she is going to be talking about her work around mapping the Great Barrier Reef. Because how can you save the planet if you don't know what's there? And this is a project that's incredibly cross-disciplinary, with lots of different diverse team members coming together. And I think it's a really exciting project that you're going to love to hear about. So please put your hands together and welcome Dr. Emma Kennedy.
Thank you, Joel, for that wonderful introduction, and thank you, BrisScience, for the opportunity. I also wanted to thank each and every one of you for turning out this evening. It's incredibly heartening for somebody like me that's passionate about reefs to see so many people come along on a Monday night to hear about what is new in coral reef science. And I'm sure it hasn't escaped your attention that many reef scientists have been feeling quite stressed at the moment as we bear witness to the global ecological collapse of our favorite ecosystem. And some of us feel a little bit like our science isn't being listened to, and I definitely can't complain about that this evening, so thank you so much for coming. So what I'd like to do this evening is to try and convince you, if you're not already convinced, that coral reefs are amazing. I'd also like to tell you a little bit about what we've been doing at UQ to map all the world's reefs from outer space. And finally, I'd like to invite you to get involved if you're interested. As a coral reef ecologist, I'm crazy about reefs, and I could very easily talk to you all night about coral reefs, but we do only have 40 minutes, so I'm just going to start with the 3 essential things that I think you need to know about reefs, and I'm pretty sure that you guys will know at least 2 of them. So the first thing is that reefs are beautiful. And they're beautiful because they are packed full of biodiversity. Despite making up less than 1% of the Earth's surface, they're home to around 1/4 of all marine species, and that includes lots of different representative animal phyla, which makes them a really exciting place for a biologist to work. Secondly, reefs are threatened, and I think you probably knew that as well. And in fact, the scientists know it very well too. We've been tracking the demise of reefs over the last 30 to 50 years, and we also understand very well what the drivers of these declines are. Things like overfishing and destructive fishing, pollution, invasive species, coastal development, cyclones, and more recently, coming to the forefront, ocean acidification and ocean warming. And nobody more than us Queenslanders understands the painful consequences of warming, having in the last 4 years seen 2 mass bleaching events on our Great Barrier Reef. And just last week, the federal government released an outlook report for the Great Barrier Reef, where they downgraded its outlook. And these kind of trends are being seen more broadly worldwide as well. So the Intergovernmental Panel on Climate Change, which is a consortium of the world's top climate scientists, last year came out with a dire warning that unless we can limit our future warming to 1.5 degrees, there's going to be very bad consequences for reefs. And even if we can limit the warming, it's very likely that large areas of reef are going to be experiencing regular bleaching events, just like we saw in the Great Barrier Reef in the last couple of years, in the not too distant future. And by the way, we're tracking well above 1.5 at the moment. The third thing that you need to know about reefs that you might not have known, but I feel is the most important thing to know about reefs, is that they are essential to humanity. Socially, economically, ecologically, culturally, we cannot live without these ecosystems. Here in Queensland, the Great Barrier Reef supports a lot of our jobs and our tourism industry, but far beyond that, the value includes things that are much harder to put a monetary value on, things like a recreational space for us and the iconic and cultural value of the reef to us and its traditional owners. Reefs also provide a lot of important free benefits that scientists call ecosystem services. So in the Philippines alone, 12.9 million people's homes are protected from waves and storm surge by the big structures that reefs will build naturally. While in Indonesia, 1.7 million people fish on reefs on a daily basis. Across the planet, an estimated 500 million people rely directly on reefs, either for their food or for their jobs. And so the fact that we're in the middle of a reef crisis and these reefs are degrading is a looming humanitarian disaster. And yet, despite these 3 important things about reefs, the fact that they're beautiful, they're threatened, and they're essential, we still don't know very much about these systems, and only 25% of the world's reefs have been mapped in any detail. So what does somebody like a marine biologist at UQ, like me, do all day? I'm pretty sure my mum and dad think this is what I get up to all day, and the reality is a lot less glamorous, even when we are on the reef. I don't know how many of you have been in a wetsuit, but it's never that easy to look that good in neoprene. And when we are out on the reef for large chunks of the day, we do often end up sitting around in our own wee. I also spend a lot of time vomiting off the side of boats. And so for any aspiring marine biologists out there, I will warn you that there's a lot more snot, wee, and vomit than I was ever expecting. And there's a lot of different types of marine biologists as well, and unfortunately I'm not the cool kind of shark wrestling type. My job would be described as probably a benthic coral reef ecologist, and that means I'm particularly interested in the biology of the benthos, or the benthic habitat, which is just the fancy scientific name for the seafloor. So that means I'm interested in all of the organisms that make up the seafloor on the coral reef. And then as an ecologist, I'm not interested just in them as individuals and their individual biology, but ecology means I'm interested in all of the interactions that these organisms are having with each other. So are they competing? Are they mating? Are they eating each other? Are they not interacting at all? Which of these are important? Which are less important? And I'm also interested in how these organisms and how these relationships are affected by the external environment. And so things like the nutrients, light, and depth become very important in figuring out where these organisms grow. But also it becomes very relevant as global warming increases temperatures, pollution increases the nutrients, and that starts to affect some of these relationships as well as some of these individual organisms. So it's really fun working in a space with so much biodiversity to try and untangle some of the complexities of this big web. And in my role as a benthic marine ecologist, I've got to work on some pretty cool projects in the past. So one was looking at this amazing pink algae called coralline algae that's really important in reef recovery as it encourages new baby corals to come and settle. I worked on a giant global conservation project that set out to look at reef conservation in the context of a changing climate. And more recently, I got to work on a project where I got to drive this giant underwater Google Street View style scooter all around the Coral Triangle, collecting images of the benthic community that we were then analyzing to look at changes in the benthic community over time. But the most exciting project that I've worked on, and what I'd like to talk to you about tonight, is a project called the Allen Coral Atlas. And this is a big collaborative project, and I've joined a team at the Remote Sensing Research Center in the School of Environment and Earth Sciences at UQ. Who are a big team of mapping experts to undertake this project, the goal of which is to map all of the world's coral reefs from out of space. And so joining a mapping team got me thinking a lot about why do we love to map? And it's a really human thing to want to map. So mapping, we do it for a number of reasons. Mapping helps us make sense of the natural environment. As a biologist, that makes a lot of sense to me. It's a way that we can simplify complex patterns. Mapping also helps us catalog our resources, which can be important for management and conservation and politics as well. Of course, maps are important for helping us find our way, and navigating around the marine environment can be tricky without maps. You don't want to end up in a situation like this. Maps also help us gain insight and make discoveries. Not just buried treasure-style discoveries, a lot of great biological discoveries have come from maps. So, for example, Darwin and Wallace's maps of coral reefs in Indonesia helped them develop their theory of evolutionary biogeography. Maps can also help us tell better stories, including scientific stories. So when we write scientific publications, they'll often begin with a figure 1, and that first figure is generally a map, and it helps us ground our research in space and time. And finally, maps bring people together without needing a language. They can help create conversations and also start collaborations. And that's a really big goal of the Allen Coral Atlas, beyond just producing a lot of mapping products. And maps inspire us as well. So I'm sure every single one of you at some point has had a play around on Google Earth, spun that planet around and decided, where would you like to go next? So to map is a very human thing. And we've also been doing it for a very long time. So since the Polynesians set off across the Pacific using star maps, our indigenous peoples also would use streaming tracks in the sky to navigate their way around the landscape. Anybody familiar with this constellation? It's Scorpius. And actually, what you might not know is that the A55 that runs from Carnarvon Gorge down into northern New South Wales follows old pathways that traditional owners would have used through the landscape, and those in turn mirror the tail end of Scorpius, as that would have been the star maps that people would have followed at the time. Of course, mapping the oceans is very tricky because it's not easy to be able to view what's underneath. The cool thing about coral reefs, though, is that they grow in very, very clear water. This is something that confused Charles Darwin a lot on his voyage on the Beagle, how these really productive systems could grow in these really nutrient-poor, clear waters. But what it did mean was that these early explorers were able to view the reefs very clearly through the water and start mapping them and also looking at their biology and the benthic communities, all the stuff that I'm interested in too. And so Charles Darwin was actually the first person to attempt a global coral reef habitat map following his voyage on the Beagle. What he did was he mapped out the distribution of different types of reefs that he found during that voyage. And since then, subsequent explorers built on his map to try and improve it, adding other reefs in, and the whole map got redone in 1912 as well. But really, since the time of those early explorers, there wasn't much improvements for many years in our kind of mapping technology. So this here is a map of the Whitsundays from 1953, and it's a composite of lots of different maps, but it draws heavily from Matthew Flinder's 1802 maps, and that was when he was the first person starting to map and navigate the reef, and he would use soundings off the edge of his boat to make his charts. And so the mapping technologies weren't really improving for a long time. A big leap in our ability to map reefs came when the Royal Australian Air Force were tasked in the 1940s with taking aerial images of the whole of Australia. And that enabled scientists like Dr. Rhodes Fairbridge, who was a geologist in WA, to start looking at reefs from a really different perspective and starting to map them in a lot of detail as well. But it was really only in the 1970s, when we had some big advances in computing, that cartographers were able to start digitizing maps on scale. And it was the World Conservation Monitoring Centre in the 1990s that started taking all of these individual maps that had been made, digitizing them, and trying to convert them into a global atlas of coral reefs. In the 1970s as well, we were starting to develop some satellite technology, and so by 2000, the Millennium Mapping Project was able to start trying to map reefs from outer space using the NASA satellite Landsat 7 that was taking 30 metapixel images of Earth. And from that scale, you can see there's quite a lot of detail that you can get with the reefs. So the combination of that satellite technology and those digitized maps have brought us to the current map of coral reefs that we have today, which is a kind of outline map, and you can see all the little yellow blobs, all the individual reefs. That map told us that there were around 230,000 reefs out there. And some of them have been mapped in a lot of detail, but because the map wasn't made in a consistent way, it was made from some satellite images and digitized maps as well. There are areas where the reefs aren't mapped quite so well. This is Heron Reef on the Great Barrier Reef, and you can see the outline here includes quite a lot of blue water, so it's overestimated the size of the reef. And this is another reef on the Great Barrier Reef where you can see it's really overestimated the size. And some reefs have been missed off the map altogether. But still, that's currently the best global map that we have. Another issue with this map for biologists like me is the extent. The outline is useful for telling you the size of the reef and where it is, but as biologists we can get a lot more information about reefs if we have more information on the bathymetry, or the depth, and also the shapes of the reefs are very important as well, and we call that the geomorphology. So around the same time that global outline map was published, scientists here in Australia were also starting to map the Great Barrier Reef using LiDAR and sonar from below the surface of the water as well. So this is an aerial image of Heron Reef, again on the Great Barrier Reef. And to give you an idea of scale, it's a very large reef. It's about 11 kilometers by 6 kilometers. There's a marine research station there, so there's a lot of science that happens at Heron Island. And with that global outline map, this is the kind of information that you would be able to get about the reef. But you can see just from the image that actually there's a lot of variability in the reef within that outline. And a lot of that variability is driven by things like the waves and the depth and the light that help dictate what kind of organisms can grow there, and the long-term geomorphology of the reef as well. And so if there's probably some divers and snorkelers in the water, you might be familiar with some of the different geomorphic zones of the reef. So if you were on this little boat here and you were diving right there where the boat is, you'll be diving in an area that doesn't have too much waves. It's quite deep, and there's not too much light, and it's very slopey, and we call this the reef slope. And on the reef slope, you get more kind of branching corals and bigger abundances of fish. If you move to this section, you probably wouldn't want to dive here because this is where all the waves are breaking. We call this the reef crest. It's the shallowest part of the reef, and there's a lot of light as well, and so you get some very hard, stubby kind of corals growing there. Back here, you move into the reef flat area, and again, that will be much more shallow and sheltered by the reef crest. And finally, the lagoon is slightly deeper, and it's typified by a sandy bottom because it's sheltered, some more delicate corals can grow in there as well. And so these geomorphic zones, if we're able to map them, can give us a little bit more information that's useful to biologists like me, because it starts to give you a clue of what kind of benthic organisms you might have growing there. And so by visiting each of these different areas and actually sending divers there, we can start to make really nice maps of the geomorphic zonation. And actually, another way to survey reefs and map them is from also sending divers into the water to do surveys, and they can manually write down what they see as they travel along the reef. We call it a transect. They'll travel as far as they can, either on scuba or by snorkeling, or else they can just take images which you can analyze later and look at different components of the benthic community, different organisms growing there. And diver surveys can help you get an idea of the benthic zonation, so the kind of dominant benthic organisms that you have, whether it's mainly corals or seaweed or sand as well. And so you can map to even better resolution if you send divers into the water and make maps a bit more like this. So the issue we've had with trying to create good coral reef maps up until today is that we either are making these really beautiful detailed maps by sending divers into the water to take a really close look at the benthic communities, but the divers can't travel very far, and so those maps tend to be very limited in extent, generally just one reef or a few reefs. At the other end of the scale, you have beautiful global maps made by things like the satellites, and they can be covering a very large mapping extent, hundreds of thousands of kilometers, but actually they're not giving us a lot of detail, and so we're just getting the outline and not much information on the geomorphic and benthic layers that are important for biologists to use. And so this kind of trade-off between detail and coverage, what we want to be doing is moving more into this area where we're able to map in high level of detail much larger areas. And so why are we so keen on creating more detailed global maps of coral reefs? Well, we like to make a lot of statements about reefs. So for example, we often say that Australia has 34,000 square kilometers of coral reef, and it's home to 14% of the world's reefs. But we only know that by looking at that yellow outline layer, and you can see there was already a lot of problems with maybe some of the reef area being overestimated there. In terms of cataloging our resources, with better maps, we're able to understand better some of those ecosystem services and what the values are to different countries, which can be important. Having detailed habitat maps can also help us scale up our observations of things like bleaching so that we can make statements about more broadly about environmental impacts. For example, we can say 81% of these reefs bleached. We couldn't go to every single reef, but you can subsample and then extrapolate them out based on the habitat. Detailed maps are also really important for helping conservation practitioners manage reefs better, set up marine protected areas. The more information they have about the areas, the better decisions they can make about where to place reefs. And finally, for biologists like me that are excited about how reefs are functioning and how they're working with detailed habitat maps, I can start to ask questions about how the reef is working as a whole, like how much fish biomass there is the Great Barrier Reef growing, where is it growing, when is it going to stop growing? But I can only do that if I have those detailed habitat maps and I can understand at scale what's happening. And so all of these are big scientific studies that were done, but they were all reliant on that global outline map, and you saw some of the issues with that map. And so even though it was the best thing that's available to scientists at the moment, it's very clear that many of these analyses could be really improved and refined with a more accurate and detailed map. But up until now, the technology hasn't been available, or the satellites have belonged to big governments and the satellite imagery has been too expensive for us to use. And we just haven't had the computer power to be able to try and map at such big scales in detail. And secondly, there hasn't been anybody quite crazy enough to undertake the challenge of trying to map all of the world's reefs in detail either. Until now, and this is where I want to introduce you to two very special scientists. This is Dr. Chris Rolfsma and Professor Stuart Finn, and they're both faculty at the University of Queensland in the Remote Sensing Research Centre, of which Stuart Finn is the director. Both of these scientists are crazy in their own ways. Chris is crazy about coral reefs, and Stuart is crazy about satellites, and both of them are crazy about mapping, and they're best friends, and for the last 20 years, it's been their vision to try and map reefs from outer space, even before that technology was really available. And so what they've been doing over the last 20 years here on Heron Reef, which is their favorite reef, is trying to develop a methodology where they take satellite products and field observations from underwater scuba divers and try and build really beautiful, detailed habitat maps, benthic and geomorphic habitat maps. And so between them, they have a lot of mapping expertise. So this is where Heron Reef is on the Great Barrier Reef. And after they've spent these years developing this methodology and they've got it working, they were able to apply it to the surrounding 20 reefs in that same section of reef and successfully map those 20 reefs as well. Remember, these are big reefs. Some of them are kilometers across. More recently, since they mapped all the reefs between Cairns and Cooktown, 237 reefs using the same methodology. And then just this year, they've undertaken a big project to map all 2,900 reefs of the Great Barrier Reef using that same methodology, which is really exciting, and we're hoping to have that really detailed reef map finished for the Great Barrier Reef Marine Park Authority towards the end of next year. But mapping all the world's reefs, every single one, is a completely different ballgame. There is a lot of reefs out there, and so we can't just apply that same methodology and expect to be able to map all the world's reefs in detail. So where to begin when mapping all of the world's reefs? And I love baking, so I'm going to use baking analogies for this. The first thing when you want to bake something really good is you need to start with some really high quality ingredients, and you need to send somebody out to get those ingredients for you. So I want to introduce you to the Dove nanosatellite. He's also called a CubeSat. I like to call him a cute sat because he's so cute. So he's only like about the size of a shoebox, about 60 centimeters by 10 by 10. And the nanosatellites were developed by a private company actually called Planet Labs. They managed to raise $50 million with their proof of concept, which was sticking iPhones onto rockets and sending them up into space. Somebody funded them, and now they have a constellation of about 200 of these nanosatellites, of these Dove satellites, out at a very low orbit, and they're imaging every single piece of Earth on a daily basis. And they take images that are about 3.5 meter pixel size. They also have one other satellite, the SkySat, which can take images about 80 centimeters, but that one has to be tasked to send to wherever they want to look. The Doves are cool because they're imaging all over the planet at the same time. And so what's cool about these little nanosats is that they are bringing back lots of data for us. And I say data, not images, because even though they look like images, they actually contain a lot of numbers. And the numbers are about the surface reflectance, what's bouncing off the surface of the Earth in terms of red, green, blue, and near infrared light. And that can be really important in helping tell us what the benthic community is that we're looking at through the surface of the water. What we can also do with that data is we can look at things like the ratio of the green to the red, green to the blue, spectra, and that can help us make maps of the depth of the bathymetry as well. So then we have information on the depth. And in collaboration with oceanographers at UQ, we also have some global wave maps as well. And if you remember from that geomorphic slide, it was light, depth, and waves that really helped determine what was growing where on the reef and about the different geomorphic zones. So that's the key kind of core information that we need to be able to start developing these maps. So we got our ingredients. The next thing that we need is a really clear recipe to follow. So this is a reef classification system or a typology that's going to determine what those map classes look like on paper. And so we're going to be developing 3 maps. The first one is just a reef or not reef map. So it's an extent map, an outline map, just like the original one that we're using, but it's produced by an algorithm rather than coming from lots of different sources. So it should be more consistent globally. So there's just 2 classes there, reef or not reef. Next, we have the geomorphic map, and so I introduced you to some of the different geomorphic zones, but actually we can go into a little bit more detail if we're being geeky about geomorphic map classes. So these are some of the different zones that we're hoping to map in the atlas. And some of these different features are really important, and having a really good think about these and what users might need to know about reefs in terms for them to make decisions about biology or conservation is really important. But it's not as easy as it looks because there is quite a lot of controversy over some of the different terminology or how some of these reef classes are defined, just because for many years we haven't been thinking globally. Scientists in the Caribbean have been working on the Caribbean reefs, Pacific scientists have been working on the Pacific reefs, and we come up with lots of different words. And so you can see those 4 different geomorphic zones that I showed you before. These are all different terms that scientists currently also use. And so we need to make sure that we're speaking the same language so that when the maps get produced, that everybody's clear on what the different map classes mean. And that can be a really tricky thing. Here's Rhodes Fairbridge again, and he's getting quite grumpy about some other scientists that he says are defining atolls differently to how he says the atolls are. And so getting this bit right is really tricky, and there's actually a full-time person on the project, that's actually me, that has to decide what all these map classes look like and that they make sense and that people are going to be able to understand the map and use it properly. So that's the geomorphic map classes. We currently have 19 classes. And then finally, we will make a benthic map as well, where we're going to get as much information as we can from those 3.5 meter pixels on what kind of benthic organisms we have there, whether it's dominated by corals, whether it's seaweedy, whether there's a lot of sand as well. And then for each of these different classes, we have to define mathematical rules about how they're defined based on some of the data that come from those original layers. So things like the depth and the slope, the colors, the spectra as well. So for example, the reef crest, we can tell the model, reef crest is always the shallowest part. It's always got the highest wave exposure, and it always goes next to the reef slope and next to the reef flat, so that the algorithm can understand how to build the map. So next, you've got your ingredients and you've got your recipe to follow. Next, you need some serious processing power. And so all of the algorithms are getting run in Google Earth Engine, because that's the only place on Earth that has enough computing power to run these kind of huge analyses. And so we'll put all our ingredients up into the Google Earth Engine, and we also put all our rules up into the Google Earth Engine as well. And it basically kind of chunkifies the information for us, and it runs everything on the server side, so our computers at UQ aren't getting worn out trying to do these really huge mathematical analyses. And next, we pretty much hit go. So we use machine learning to train the algorithm how to map from some training data. So using Chris and Stuart's original mapping methods, our mapping team makes small maps that we're able to make. We upload those to the Google Earth Engine. It looks at the maps, then it looks at the other data, and it extrapolates what it sees to the other regions that haven't been mapped yet. So it's pretty much using a little bit like facial recognition technology. It's able to look at the data and start to build the maps, and we're doing that on a region-by-region basis because reefs vary quite a lot in different biogeographic regions. So you'll start with kind of inputs like this, like data layers on the different spectra and bathymetry, and end up with maps that look like this, the geomorphic zones and the benthic zones as well. Next, you wouldn't undertake such a big baking project and then just try and feed it to people without tasting it yourself first and checking it. So we need to do a little bit of validation to make sure that the maps make sense. So this essentially means that we need to go to some of the pixels that we see in the satellite images and check physically what's under the water in each of those areas to make sure that it's making sense, our map, and what we're producing from the data. So going into the field and collecting more data on the benthic community helps us validate maps that we're producing. It also helps us build those training maps as well that we feed into the machine learning. And it's also important just to be out there monitoring and keeping an eye on reefs, because there's just not enough scientists that are able to go and visit all of these reefs, and so that kind of information will be used by scientists as well. And so this is a big part of my job, and when I tell my mum, they're sending me off again to go and do some field work and check, they basically tie a GPS to my butt, and I have to go and go to the pixels and see what's underneath the water. I'm pretty sure she thinks this is what I'm up to all day long, and the reality for anybody that's ever done any work on the Great Barrier Reef isn't always as fun as that. This is our last field trip to the hardline reefs earlier this year, and it was like pretty grim conditions out there. Alex doesn't look too happy about having to go in the water that day. I talked a little bit about all the biodiversity on the reef as well, and sometimes that biodiversity wants to come and help out when we're in the field, which isn't always that fun either. So here's a little olive sea snake that was really keen in helping us with some of our photo transects on our recent trip as well. It's very beautiful. So essentially, there's a GPS just in a little bag that's on the float. We tie the float pretty much on a piece of string to us, and then we go along swimming as far as we can across as many geomorphic zones as we can get, which sometimes means doing some pretty hairy swimming across the crest, imaging as much as we can to try and collect as much information over a bigger area as we can manage. And then after a whole day of swimming, and we've sometimes had to swim several kilometers, we'll come back to the boat and we'll upload all that GPS information and all the images as well. We'll link the photo images to the GPS points, and we can start analyzing some of the images as well. And this isn't me tipping from side to side. This is actually how we were trying to work. And I didn't have to do any data entry that day because I was vomiting so much. Everyone was doing it for me. We're really lucky because obviously you saw how many reefs there are in the world. Our field team's just not big enough to visit all the areas, and so what we've got is lots of lovely people all around the planet that have been volunteering to help us. So we've been posting them shoeboxes out that's got the camera, the GPS, the float, the little piece of string, the instructions of everything that they need to do, and they've been going to their local reefs and collecting those images and linking them to the GPS and analyzing them and sending all the data to us so that our maps can be better, because the more data we put into the maps, the better and more accurate the maps become. So finally, if you're undertaking such a big baking project, you need a team of cooks. And so this is our team at UQ, and it's a really, really diverse team of people from And they've all got really different skills. So some of us are really heavily involved in the fieldwork or running the logistics of the project. We've got expert mappers. We've got guys that are wave modelers or in charge of processing the satellite imagery, uploading it into the Google Earth Engine, or analyzing it in there as well. So it's a really fun and diverse team that I'm representing today. And of course, more broadly, this is a big international project. So it's not just the UQ team. We're in charge of making the maps itself, but we also have partners right across the planet. So Planet are based in America, and they're giving us all their beautiful nano satellite imagery. Arizona State University have been pre-processing some of the data. They're also looking to see whether they can detect changes on coral reefs in space over time as well, using some of those planet images, which is another really exciting part of the project. Vulcan are a big philanthropic organization who funded the project, and National Geographic have been helping us with getting other field teams collecting data for us, and also checking in with people, checking that the maps that we're making make sense to people in different areas, and that they're going to be useful and what they need out of a reef map as well. And of course, teamwork also needs inspirational leadership, and so Vulcan is a philanthropic organization of a man named Paul Allen. He was the co-founder of Microsoft, and he was crazy about the ocean, and it was his vision to build this atlas, and that's why, if you're wondering, it's called the Allen Coral Atlas. So we sadly lost him at the beginning of the project, but this is hopefully going to be a real legacy for him. So, where have we got to so far? In the first year, last year, we just did some little pilot maps to make sure that they worked. And then this year, we've also mapped the Cairns to Cooktown sector. Sometime this week, it's really exciting, our Fiji map is going to appear on the website, so you should check it out. We've been waiting, hopefully, in the next couple of days. And then we're going to be moving on to Palau, and then the Caribbean and East Africa as well later this year, and then some of the other regions next year. And I talked a little bit about the reasons why we map and the mapping products, and essentially we're producing these maps because we want to help scientists and conservation practitioners and policymakers to be able to make better and more informed decisions about reefs using these maps. But beyond that, we really wanted to start conversations, bring people together, and make the Allen Coral Reef Atlas portal a kind of a hub for the community. And so other big organizations have been donating some of their data layers, so things like the bleaching forecast for reefs is going up there as well, so you can check on your reef and see if it's going to bleach anytime soon. And all the data is going to be freely available for anybody to use, and we want it to be really easy to find and and easy for people to download that data and use it for free. And there's also going to be options for some citizen science organizations to also upload their data to help so that we can continually be improving the maps, particularly in areas where we have less data. So the goal is to kind of build partnerships, and this is where we'd really like you to get involved as well. So if you are involved in conservation or coral reef science, or even if you're just interested, I'd really encourage you to hop onto the Allen Coral Atlas website. We blog a lot about what we're doing as well. You can follow our progress. If you know people that might use the maps or just want to visit your favorite reef, check that we've been doing it right, give us some feedback on things that you'd like to see. We want this to be a kind of big collaborative effort, and we want the maps to be useful and used. If you're interested in getting more stuck in helping collect data, there's a number of different things you can do. So Coral Watch is a great way, if you like snorkeling, to get involved in helping collect bleaching observations. So I mentioned before that there's just not enough scientists to be able to get out to all the areas that are being affected. And when these big bleaching events come around, we're often don't understand enough about how the reefs are responding to heat events just because we don't have enough people in the water collecting information. So you can help through that. If you're really into diving, you can even sign up with Reef Check Australia, and you can actually learn how to help monitor reefs in Australia. And if you don't want to get your feet wet, the virtual reef diver is a really fun way you can get involved, and you can analyze benthic data from home, looking at some of that imagery and having a play helping scientists understand more about the Great Barrier Reef. And I'd also encourage you to, if you're interested in reefs, to read more about them. If you haven't seen the film Chasing Coral yet, that's on Netflix. It's a really nice overview of the coral bleaching crisis and what's happening with corals in the world at the moment. So watch that, have a conversation with somebody about coral reefs, and just use your voice. And the other thing that I'd say is really, we're aware now that reefs do face a lot of different threats, but the biggest threat at the moment is the fact that the ocean's warming so fast, and we're going to be seeing these bleaching events more and more. And obviously we're seeing lots of bushfires at the moment as well. Warming's a problem for all of us, and so really the only way that we can save reefs is to reduce our carbon footprints and pressure our leadership and our governments and our politicians to help us do that as well. And helping reduce your carbon footprint can also help save a lot of cash as well, so it makes sense. I sometimes get quite worried about the outlook for reefs, and I sometimes wonder, like, can we make a difference? You know, we're not tracking well towards our Paris climate goals. So I kind of wanted to finish the talk on some inspirational quotes from two very inspirational people. So I already introduced you to Paul Allen, who was the founder of this project and the only person crazy enough to have this vision to make a map of all the reefs. And Ruth Gates was a marine biologist. She was a personal hero of mine, and she was the director of the Hawaii Institute of Marine Biology, and she was also co-founder of this project, and she was just this incorrigible optimist, and she really believed that science alone can't save the reefs, but it does require big social shifts in the way that we think about things, but like all of us together, she really, really believed that we can make a difference, and that was very inspiring. So that just leaves me to thank, this is a big team project, so it's not just me, these are all my teammates that are helping make this map, and thank you all for coming along and listening.
Thank you, Emma, for an inspiring talk and lots of interesting things there to touch on. So we will take some questions now. So if you have questions, write them down in the question slip, post them to Twitter, and we'll come down and collect those through the aisles. Already a couple of questions come through. Housekeeping, of course, if you want to be kept up to date with future BrisScience talks, make sure you head to our website to sign up, or to Facebook, and keep up to date with everything there. And of course, we post on Twitter regularly. Next month, we are back with a talk on epidemiology and vaccine development, and how we can develop vaccines more quickly and potentially stave off global epidemics in the future. So I think it's going to be a really interesting talk, and lots of cutting-edge medicine to talk about there. So make sure you join us for that. Questions now. Oh, we've got some coming in here. Fantastic. And I have some on Twitter. So let's go to Twitter first, if you're ready for some questions.
Yeah.
Brilliant. First is, oh wow, okay, there's a lot more now. Okay, first question is from David. We've had a couple of questions about the CubeSats.
Yeah.
So I'm going to start you on the technology stuff first. So the question from David is, are the Dove CubeSats designed for ocean imaging, or are they general purpose imaging ones that can provide useful data? And would you design them differently if doing it just for the reef?
That's an extremely good question, thank you. And the answer to that is they're not just for the ocean, they're actually for the whole planet. And what's been really cool is there's other scientists doing other projects using them to track things like deforestation across the planet, because the thing that's is cool about them is a lot of the other big satellites only pass over maybe once every 10 days. Sometimes they have to be tasked to visit an area, but Planet are kind of spying on the whole planet at the same time. And so we're really starting to see, for example, things like the bushfires in the Amazon. And here I was looking just today at some of the bushfires in Lamington using the planet doves. So they are much better actually at looking at terrestrial environments, and mapping under the water is pretty tricky. You have to have like a really, really like clear day essentially, and where we do have really murky areas with turbid water, if at certain times of the year it doesn't get any less murky and it's murky like that all year round, then we're never going to be able to map that reef perfectly. So yeah, if you could design the dream satellite, it would be one that would be able to like look under the water, but unfortunately water's very reflecty, and so a lot of that spectra gets reflected, and that's what we're picking up.
Great. Question from Howard, also on Twitter, around the how and, so made much comment on the how and why of mapping, but not as much on how the maps might monitor change.
Oh, and if I had more time, I would have loved to talk to you about that in a lot more detail. And so, yeah, the cool thing about the doves is that they're imaging every day. And so there has been some work done to see whether we can see coral bleaching from space, but it's very difficult for a number of reasons. Firstly, because corals and algae both photosynthesize, they look a little bit the same from space, but if they go, so you have to be able to be there at the right time to see everything go white, because if it dies, a dead coral with algae growing on it looks very similar to a live coral from space. But what we have been trying to do is see whether we can detect those very fine-scale changes automatically and have a kind of auto-alert system. And so what's happening at the moment in Hawaii is they're about to have a horrible bleaching event. All the predictions say that the corals are all about to bleach. And so we've sent the CubeSat, the high-resolution satellite there as well. We're trying to see whether we can somehow mathematically get the satellites to notice when there's small shifts in the color and the whitening. But essentially, it should be possible, and that would be a really valuable thing to know, because often these areas are bleaching, and we don't know which areas. We've got information on how the planet's warming, so we have predictions about, we think this area is bleaching because the water's getting very hot, but we don't actually know how the corals are responding. So that's another big part of the project that's being led by Arizona State University that I didn't really talk about. Good question.
A lot more behind the scenes. Question from Twitter. Andrew asks, what kind of information is collected by divers except imagery? Temperature, light level, etc.?
That's also a good question. So there's a lot of different things that you can collect. The thing that I come from a kind of ecology background, and what we like to do is monitor changes in time. So we do a lot of like experimental work where we set up experiments on the reef and then look at things like we put temperature loggers and light loggers down there and then see how organisms are responding over time. And this is a slightly different project because we're going to as many different areas as possible to improve the mapping. So instead of looking at one area in detail over time, we're trying to look at a lot of areas. So there's less time for me to be able to set up the experiments that I'd really like to run. But one cool thing we're trying to look at is we know that the complexity of the reef is very important. So it's this kind of beautiful 3D shape, but when a lot of the reef dies, it goes flat. And we know when it's really complex, there's more hidey holes for animals, and it's a really good indicator of biomass and health as well. And so we've set up these stereo videos where we can start to sort of map the 3D complexity as well as just straight sort of benthic imagery as well, to get a sense of how complex these reefs are and how healthy they are. Another thing that I'm really into is I collect sound. So many people don't know that reefs are actually really noisy places, and you can get an idea of the biomass and what's living on the reef by putting a hydrophone, like a recorder, down into the water and listening to all the animals. So I do that as well whenever I can.
What are the animals saying?
Good question. They kind
get out of my house.
They sound a bit like sizzling bacon, kind of like a frying. It's really, if you're ever snorkeling, or diving, have a listen, because it can be really, really noisy. And the fish all kind of grunt and burp at each other. It's a very noisy environment because sound travels so efficiently underwater, and so scientists have gone into that space thinking very visually and not realizing that actually a lot of the organisms are communicating with sound, and it's a very noisy place, surprisingly noisy.
You mentioned drones. Damien on Twitter asks, to what extent could submersible drones be used to photograph the reefs to replace having to do it in person?
That ruins all the fun. I like going to dive on the reefs, but yes, certainly more and more that tech's being developed, that they're able to send drones to do like a lot of the lot of that work as well and reach areas that divers can't reach, which is valuable because when you've got like a tank on your back, you can only stay down there as long as your tank of air runs out, and so you're quite limited, whereas more and more now, I think QUT are developing some underwater robots, and there's some really cool stuff in that tech space happening at the moment.
How long can a drone stay underwater for, do you know?
I don't know. I'm not sure. It's a good question.
Yeah, well, we don't want to take away the fun part of the job of actually getting to dive under the reef. We're almost out of time, so I've got one more question from Kelly, who asks, does the mapping show up pollution, such as plastics, in these environments?
That is also a really good question, and some things that we've been able to see on the planet imagery is things like big wrecks of boats. And so recently, earlier this year, back in February, there was a boat called the MV Solomon Trader that crashed into some really pristine reefs on the Solomon Islands. But nobody really knew about it, and the governments didn't really want to say too much about it. Nothing was done, and so this boat was sat on the reef for ages, and through satellites people were able to keep an eye on it, and they could see the oil leaking out. And so more and more you can, with this ability to kind of spy on the whole planet, there's a bit more accountability and things can happen faster. So in the case of this particular wreck, it sat there for a very long time, and there was plenty of time for people to remove it before the oil started spilling out. And so we're hopeful that we're able to start helping a bit more with disasters like that using the nanosats as well, respond a little bit faster and help protect reefs in that way. Yeah.
Well, good advice for us all to go up and tidy up our backyards. You never know who's watching. Starting with the Great Barrier Reef. On that note, I'm going to wrap up tonight's proceedings, but could you please put your hands together for a fantastic talk. Dr. Benthic Ecology from UQ. And we'll look forward to having food and drink outside, and see you all next month.